last time we looked at classical scattering, where we had some incoming particles, and we discussed what happens if they hit a hard sphere target of some size r. And we discovered that, and again, it's convenient to kind of parameterize things with, of course, this is kind of the direction of the incoming particle beam, and then you're looking at the scattered particles in some direction, k prime. And you want to set up your coordinates such that the incoming beam is parallel to z, so that then this angle here, theta, is the same as the spherical angle that we would normally use in spherical coordinates. So this is a convenient way of parameterizing things, and we found that classically the total cross-section for the scattering is the kind of surface area presented by the target sphere to the incoming particles. This is like the total area that's seen by the incoming particles. And we also found a constant differential cross-section. This is the differential. This is the cross-section associated with scattering in a particular solid angle. We found that this was 1/4 r squared. And that's the classical situation. And now we will try to understand what happens quantum mechanically. And so instead of classical particles here, we know that we have some wave function, which, if we do this properly, it would be a wave packet, and we would sort of package it in some envelope and have it come in with some momentum, which again has to do with the wiggliness of the wave inside the envelope. But we know that we can understand a lot of properties of scattering by just looking at not the wave packet description, but just the wiggles in here, the stationary states, without thinking about the time dependence exactly. So the incoming wave is going to be some plane wave along the z direction. And we know that this will have some energy associated with it, which is just this. This is just the kinetic energy of an incoming particle. So it'll come in, and of course, it'll encounter some target. And the target we're going to describe with a with some kind of potential, right? There'll be some potential here, and so instead of the sphere, we will have some potential. Now it could be, if it's a hard sphere or something like that, we could kind of incorporate that by using an appropriate potential. We could say that we just have an impenetrable sphere, so that we could do something like that, and we'll look at that. So in that case, you would have like a hard wall when the little r is equal to big R, the radius. You'd have the potential just be infinite there. And then, of course, we want to see what happens far away. And again, far away after the thing has scattered, what will actually happen? It'll come in here, the wave packet will distort in some fashion due to the potential, right? Something will happen to it, and then it'll come out, and due to the spherical symmetry of the potential, it'll be convenient to analyze what happens after the scattering occurs in terms of spherical waves. So we'll have our spherical waves, which are proportional to E to the I K R now, with the R, the radial distance away from the center of the potential. And so these will be the outgoing waves. And they'll have some angular dependence too. So it's multiplied by some function of theta and phi, where these are the spherical polar coordinates as defined away from the z-axis, which again is kind of assumed to lie along this direction. So we'll explore all that, and we'll see how it goes. And of course, this should be careful there. This is going to be some k prime. This is the scattered momentum. So this is the kind of general idea, and so we should begin by looking at the incoming part. This incoming part. And for the incoming part, we want to relate the stationary solution here, the plane wave, to our notion of incoming particle flux. And we know that associated with any plane wave like that, there will be a probability flux, right? Something we looked at briefly in the first semester. There's a probability flux associated with the plane wave, and it's just given by h bar over 2mi with these cross derivatives, or this actually a cross, but this combination of the gradient and conjugate of the wave function. And if your wave function initially is just some amplitude times e to the ikz, the plane wave, then you can plug this into here, and what you'll find is that this is equal to a squared magnitude h bar, and it's going to be the only gradient that survives is along the z direction, which is the direction of the k vector for the incoming particle. So if we generalize a bit, if it just for us k vector is always k times z hat, but we could just write it in terms of the k vector like that over m. And we recognize this as, this is the momentum, the incoming momentum divided by the mass. So this is the amplitude of the plane wave squared times the velocity of the particle. And this must be proportional to just the incoming flux of particles. This must be, since a squared is going to be a probability, right? And the velocity, then if we multiply by the total number of particles that are coming in, we should get the flux. So this is proportional to, I should say, the incoming flux that we discussed last time. Okay, so that's good. And now we want to understand what happens when there is a potential. So any questions so far? Okay, so when there's a potential, then of course we're interested in, so when we add a scattering from a potential. And we're imagining now that, our target is stationary. It's a very large target. It doesn't move. And so we only have to worry about what happens to the incoming particles, which are small. And if the target doesn't move, then we could just model it as a just a potential function, some v of r. If you had the target move, you could do other things. You'd have to do something else, right? If the target's moving, you'd want to go to a center of mass frame, and then you'd have two different coordinates, one for the target and one for the incoming particle. And then you'd have to write down the total energy, which is the sum of the kinetic energies for the target and the initial particle. And then you could change coordinates to center of mass plus a relative coordinate. And then maybe you could argue at the center of mass coordinate that remains stationary, and then you could write a Schrodinger equation in terms of the relative coordinate, and then maybe you'd get something quite similar to what I'm about to write down. But we're not going to do that. We're just assume that if we're just dealing with scattering from a stationary target, so we won't worry about moving to centers of mass frames, things like that. So if you have something like that, then the equation we're interested in solving is just the usual time-independent Schrodinger equation. And the solutions are going to be labeled by the wave vector, the momentum. So that's the idea, and we're going to try to look for solutions to this that are a combination of the incoming wave and the outgoing spherical wave, as I mentioned. You can show, and we'll do this later, that a form of a solution to this, and we'll do it later when we solve this equation more formally, using a Green's function. You can show that a solution has the following form, that you have two different kinds of solutions you can write down. And they have the following form. Again, second order equation, right? We expect two different kinds of solutions. So we can show that solutions, let's say it properly. So we can show that we have solutions which we'll label psi plus or minus k, that behave as follows. For r much bigger than r interaction. So we're imagining we're trying to understand what these solutions look like far away from where the interaction with the target happens. So this is, we're imagining our potential V of R has some kind of characteristic size, some range over which it acts, which we call R interaction. And then we're just looking at the solution to the Schrodinger equation far away from that. And of course, the Schrodinger equation will depend on the details of the potential, of course, but far enough away, the form of the solution that we'll have is as follows. There will be some amplitude, and there will be an e to the I k dot r, and this will just be the incoming part. If we have the wave vector along the z direction, so there will be some kind of incoming plane wave. Then there will be some angular function, which might depend on the k vector we're putting in, and it'll depend on the angle at which we're looking out at this function. And then we will have both incoming and outgoing spherical waves. So I'll argue why. I'll show you why you get these kinds of solutions later, but for now we're just going to assume that that's what you have. And yeah, so that's the idea. So now we can do the same thing and try to see what happens to the flux now from this solution. And again, the idea is that this part's the incoming part, so any flux that comes from this piece, that's the part that's associated with the scattered portion of the solution. So we want to know what the flux is associated with that piece. And you see, this is kind of nice because there's this 1 over r here. When we take the gradient of this, so let's take the gradient of these spherical wave parts. So let's look at the outgoing spherical wave, which would correspond to the stuff that gets that moves out away from the target, which is what we'll be detecting in our detector. This is the scattered portion. Goes out. We typically throw out the incoming spherical wave. In a scattering problem, this is quite similar to the fact that we don't, remember in one-dimensional scattering, we always throw out the wave that comes from large x from that direction. In a 3D problem, it's sort of the same. You would throw out the wave that comes in from infinity. That's not the incoming wave. So there's always an incoming wave, but if we take care of that here, then all of this stuff must be the scattered portion. So we typically toss out the incoming spherical wave. So we're only left with the IKR, not the minus IKR in that exponential. So that's what this is sort of we just keep the outgoing part. And if we take the gradient, which will help us see what the flux is, we take the gradient of this part, then what happens? Well, you'll get a term that hits this exponential, right? And then you'll get another term that hits this R, but that part won't, that part will give us something that goes like 1 over r squared, which will be small compared to the first term. So the first term is I k r hat e to the I k r over r times this angular function plus something that goes like 1 over r squared, which we can ignore because we'll be looking far away. And so in general, then the flux associated with this portion is just going to be the amplitude squared h bar k over m, and then it's going to be the magnitude of this. So this is out. This is the outgoing flux, and again, this is the incoming flux. It'll be this guy times r hat over r squared. It'll just be you could just calculate with this by plugging this form in. For the gradient, you get this. Basically, everything becomes squared, right? Well, this goes away because of the complex conjugates, so you get 1 over r squared, you get this guy squared, and you get the amplitude squared, and then there's h bars and m's due to this factor out in front here. And the gradient, so you basically get this. So very similar, except now you have this extra angular dependence F, like that also gets put in here and squared. So that's the probability flux that comes out from the target due to this outgoing spherical wave. And now all we need to do is calculate what actually you would detect due to this outgoing flux. But any questions so far about this? This is just like setting up the scattering problem in 3D. And instead of having the 3 regions that we looked at in 1D and 3D, you just have an incoming plane wave along some direction, and then everything else is just a spherical wave. And it's just a convenient basis. It doesn't have to look like, you know, a perfectly symmetric spherical wave, because we have this angular dependence that'll, you know, depend on the details of the scattering, the potential. So this is still, it's a very general kind of development. It's just convenient to work in spherical coordinates when you're dealing with sort of 3D scattering. But okay, yeah, so interrupt me if there's questions. So what's the idea now? We can imagine this, what the idea is that we have this potential and we have this outgoing flux due to the scattering from this potential. And we're gonna detect it, right? We're gonna detect it with some detector. We're gonna detect it in some solid angle, d omega. So we want to know the number of actual particles that we detect due to this outgoing flux. And the number of particles we detect there is just going to be the probability flux dotted into the surface area kind of presented by the detector. And the surface area presents is going to be r squared times d omega in that r hat direction. So what we get is we have, for the surface element, we get here, well, let's just write down J out first. It's amplitude squared h bar k over m, and we can identify h bar k over m. Let's identify it right away. This is just the velocity, right? It's the momentum divided by the mass. And then we have our angular dependent function squared. And then we would have r hat over r squared, but that's dotted into the surface element, which is r squared d omega r hat. Because this is, you know, we're imagining the particles coming into this detector, which is out here at some radial distance, a little r away from the target, and it's presenting the surface area in some solid angle, and the surface area of that would just be r squared times the solid angle. That's the surface area it presents. So we just dot the incoming flux into the surface element, and we see we just we get a nice thing. We get that this is equal to the r squareds cancel, and in here we could identify the incoming flux, right? Let's see. Let's pull back a little bit and see what we got here for the, remember this was proportional to the incoming flux. So there's a total number of particles involved, which we have to multiply both by, but if we just say that this is the incoming probability flux, we could just keep those units. So let me put an equal sign here and just define this as the just incoming flux. You have to multiply by the total number of particles you have to get the actual number flux, but It's fine to not do that. Then this becomes the incoming flux times this function squared, and that's times d omega, right? And if you go back to our definition of the differential cross section, then you'll note that from this relationship, we can immediately conclude that the differential cross section is in fact just equal to this amplitude squared. And this is a very important formula. We'll give it a double box because it connects a quantum mechanical object, namely this amplitude of your Schrodinger equation solution, to a measurable quantity which we calculated in the classical case for a hard sphere, this differential cross section. So this really tells us how to do the quantum mechanical problem, and maybe we'll be able to connect it back to some of these classical results to build some intuition. And again, the idea here is that this is a function of the incoming momentum, and then you're looking at the solution. So it's a kind of funny solution. The k vector refers to the incoming portion, the incoming momentum, and then you're looking at this solution at some angle omega that's away from the incoming direction. So you would write this as sort of e to the I kz, and then this guy would be, or if you want e to the I k r cosine theta, and then this guy, this omega, would be the spherical coordinates, associated with the origin being at the center of the target, and you're looking at some angle, away from the target, where your outgoing particles go. And so this notation, it tells you a lot. It says, okay, there'll be an amplitude. It'll depend on the incoming momentum, and it'll depend on the angle at which you're looking. And again, it all just comes from solving from a particular solution of the Schrodinger equation. And there's a bunch of, going to be these solutions for any kind of incoming momentum that we have. That's why we label the solutions with this k. But the function you get will be a function of like where you're looking away from the target. So hopefully that makes sense. But as you sort of do homework problems and we'll do examples, it'll start making a little bit more sense, I think. Okay, but any questions? Okay, so this is the setup, and now we're going to actually try to solve the Schrodinger equation. So that's the next step, and so I'm going to clear this because it's sort of, this is just the setup. This is the general stuff that you need to know. But now to actually solve particular problems, we'll need to, actually find solutions to the Schrodinger equation, this guy. All right, so I'm gonna clear this. So let's look at solutions to the Schrodinger equation, and again, we'll consider for now spherically symmetric potentials. So spherically symmetric scattering from some potential V of R. And we already know how to do that. We know how to deal with spherical symmetry. we write our solutions as follows in spherical coordinates. We have an expansion in the spherical harmonics. We have some radial wave function multiplied by, our favorite YLMs, like that. We know that's the general form of the solution. We even know what the equation is for the radial pieces. The radial pieces satisfy this Schrodinger equation. This is all from last semester, and we were looking at, and actually this semester too, it's the same thing we did for solving the hydrogen, the Coulomb potential. And again, we're looking at problems where you're coming in with some kinetic energy. So this 2me over h bar squared, it's convenient to just denote this as k squared, because that's what it is. So we're looking for, and I should also say spherically symmetric elastic scattering. And we'll mostly deal with elastic scattering. I'll mention something about inelastic scattering, but for the most part in these quantum mechanical problems, we'll deal with elastic scattering, meaning that the energy is conserved, right? So if you're coming in with some incoming particle with some kinetic energy related to a wave vector magnitude k, then that energy is conserved. So that is the energy. That's why we can substitute 2me over h bar squared as just k squared. Okay, so what else do we know? We know that the actual scattering problem itself for a spherically symmetric potential, it'll also have some, cylindrical symmetry. So there is nothing in the problem to specify the phi direction. There's nothing that breaks the phi symmetry. You have an incoming thing along the z direction, right? And you have some spherically symmetric potential V of r. I guess I drew like this. So there's symmetry around the z-axis. So we also have that there's no phi dependence for our solutions. So really what we're looking for are solutions that only depend on r and theta, how far away you are, and then again, theta is just a very convenient in this coordinate system. It's just the angle away from the incoming direction, just that spherical angle away from the z direction. So this we can write as sum over r. And if we just keep the portion of the spherical harmonic that, sum over L. If we just keep the portion of the spherical harmonic that depends on theta and not phi, we'll be left with these guys, the Legendre's PL of cosine theta. So that specifies our solution a little bit better. So now what we do is we're going to try to connect the solution to that general form that I told you about just before I erased the screen. I told you that far enough away, we should get that psi is equal to some amplitude, e to the I kz plus some angular dependent function, e to the I kr over r. And we're going to try to see how the solution of the Schrodinger equation actually gives you this far away at large r. We're going to try to identify all the pieces. How do these use, connect up with this guy and the incoming wave? I'm going to try to build that connection. So the way you would begin is by looking at a free particle. Which has, v equals 0. You can actually solve that differential equation. Now it becomes quite a simple differential equation. Well, simple-ish. It just becomes, if we don't have any potential, right, then everything out here, it's just it's a little bit of a tricky equation, but the equation for U, so I'll call these ULs, these are free for the free particles because there's no potential. This is a second order ordinary differential equation. It's got this 1 over r squared piece. And does anyone know what the solutions to this equation are? Or special functions? Does anyone know what their names are?
Bessel functions.
Exactly right. They're the spherical Bessel functions. That's right. And there's, of course, 2 of them because, again, second order equation, so we have 2 solutions. And so what we can write down the general solution just as we would for any differential equation. It's given as a, and remember, it's a little bit tricky. L is kind of coming along for the ride, right? This is, and again, we're dealing with actual angular momentum due to sort of coordinate changes. So L is, some integer 0, 1, 2, 3, and so on. Just like you would treat a rotation, just like on the homework. So each solution here has this label L, and Chet says these are just the spherical Bessel functions. There's the J1 and the N1, and they're functions of K times R. And A and B are just arbitrary coefficients. So that's what they are. That's just the solutions. And I can even tell you what they are. I can give you a definition of how to find them. To find the J's, any nth one, say, what you would do is a function of any z. You would take minus z raised to the nth power, and then you would take a bunch of derivatives of this form, acting on sine of z over z. And the other guys, the n's, that's kind of awkward. I made it n. Fine, well, maybe we'll do L. It makes it a little nicer. Okay, L. These guys are similar. It's minus z, the L, and then you take the same derivative and act with it L times on cosine. So roughly speaking, they're kind of oscillating things. And they're oscillating, and you can actually, there's a lot of books about them. They're special functions. Again, these are called the spherical Bessel functions. You can plot them in Mathematica. And the most important property that we'll be interested in is what did they look like for large R or large Z. So what do these look like for, KR, which is dimensionless, much bigger than 1? What do these functions look like? They have some asymptotic forms. J of L KR looks like sine KR minus L pi over 2. And you can derive these asymptotic forms from the definitions of the spherical Bessels. Maybe I'll do it in recitation, but I don't really think it's particularly interesting. It's just worth it. You can just look these up. People have studied these special functions for a long time, and they discovered that, for large values of the arguments, they have the following behaviors. There's some phase shifts here in these cosines and sines, but otherwise, they just have this form. So what does it mean? It means that far enough away, these guys are just sums of sines and cosines, right? You have a bunch of sines and a bunch of cosines. There's a 1 over KR in both of them, so one of the r's cancel. So you get like a constant times a sine plus another constant times a cosine. So that means that if we look at what happens to this free particle solution, again, far away in this limit, this thing, as it's just going to be a sum of sines and cosines, we can write that alternatively as just we can write that as just a single sine function, right? KR minus L pi over 2. And then instead of adding the cosines, we can just say plus some L-dependent shift. This is the same as writing A cosine or writing plus B cosine, right? So I can either write arbitrary sums of sines and cosines with 2 unknown coefficients, A and B, or I can write it as a single sine with 2 unknown coefficients, A times delta L. And since they're arbitrary, I can free to parameterize my solutions any way I want, right? So I can parameterize them either as cosine plus sine, or I can do it as a single sine, but with the arbitrary phase shift. It's the same thing. There's still covers all the possibilities. Okay, so great. So now we know that far enough away, our free particle solution looks like this. But we know we should be able to connect this now somehow to the incoming plane wave, right? Because we know if there's no potential, what does our general solution look like? Well, it should just be this guy. Should just be the incoming plane wave. If there's no potential, then there's no scattering, so this is gone. So we have to connect it back. So this is the first kind of result. And now we have to see what happens to the incoming plane wave. And the incoming plane wave is going to be e to the I, k dot r. Again, k is along the z-axis, so this is I k r cosine theta. And this has an expansion in terms of Bessel functions. You can also just look this up. It's an expansion of a function of this form, e to the I k r cosine theta. You can expand it, and what you get is the following. You get a sum. It's sort of, you can expand it in spherical harmonics, essentially. It's where the spherical Bessel comes from. So again, if there's no phi dependence, then the spherical harmonics are just the PLs, like we had here. So you can just look up how you expand a plane wave in spherical harmonics. And what you find is that expansion is given by 2L plus 1. Then it's I raised to the lth power, the imaginary I. Then it's a spherical Bessel, JL, K, R. And then it's the PL cosine theta. And so, well, now we can see what happens at large R again, right? Again, for KR, much, much bigger than 1, we know how the spherical, how the J's behave, right? So this must be equal to L0 to infinity, 2L plus 1, I, L. These guys become sine KR minus L pi over 2 divided by KR. This just, comes from this guy, just the asymptotic form for the spherical J. And we have, of course, the PL cosine theta. So now we can sort of see the connection, right, a little bit better. We see what the relationship must be between. And again, remember that this solution here, this is the U of L's, right? This is U of L over R. Remember this U of L over R. So this part here, let me outline it. This must be the U of L portion. For an incoming plane wave. So we can connect it to this. You see that you'll have a certain value for these ALs, has to be L plus 1 over K business, times this I to the L. So you can make this connection and see how this solution for which values of AL and delta L here, delta L has to vanish. That's what you would get for an incoming plane wave. That's the solution we're looking for. So let's see, what else? So now we've identified the plane wave part, and now we want to do a little bit more work to figure out in terms of solutions to the Schrodinger equation, how you get this F portion. So we built the connection to the incoming plane wave by expanding the exponential and looking at the free particle solution. And now we just have to figure out what happens when there is a potential. What do we do then? So let's look at, and this will lead us to a discussion of phase shifts. This kind of next big topic. By the way, I didn't mention this, but when you expand everything out in terms of L in the spherical harmonics, or in this case, these Legendre polynomials of cosine theta, these expansions that we do here from the point of view of scattering, this is called the partial wave expansion. And every value of L is a so-called partial wave. I forget exactly what the origin of the phrases, maybe something like, because you're, essentially the main formula comes down to expanding a plane wave into a bunch of different pieces. Maybe I think that's why. I'm not exactly. I forget why. I knew, but I forgot why it's called a partial wave. But yeah, maybe I'll tell you next time. But that's just what they're called. And just as in orbitals, right? For when we were solving hydrogen and so on, the different L values have letter names. So like L equals 0 is S wave, is the S wave scattering. L equals 1 is P, and so on, just same as the orbitals. So yeah, let's talk about phase shifts. So again, the idea is instead of let's go back to our general solution. What is it going to look like? Well, it's going to be again amplitude, then e to the I k, and r cosine theta, and we know how to expand this in spherical vessels already. I just showed you. But then you also have this angular function, but it's an angular function, and an angular function, we can expand it using the spherical harmonics because they're complete. Any angular function you can expand in spherical harmonics. And moreover, by the symmetry, we know that angular function only depends on theta. So that whole amplitude is going to be some sum over the partial waves again, the L's, of PL cosine theta. It has to be that. Because the Legendre polynomials, they're complete. They form a complete basis for functions that depend on theta. Or more specifically, they form a complete basis of functions, a complete basis for functions that live on the interval -1 to 1, right? And cosine theta lives between -1 and 1, and so any angular function you could represent as some sum of some coefficients times the Legendre polynomial of cosine theta. And you have the outgoing spherical wave. So all we have to do now is just figure out what these F's are. We know from the expansion, from just properties of the completeness of the Legendre polynomials, that F of L, there's a normalization associated with this, but this is just like from the completeness property of the and I should probably put a little K label on these F's, but it's there implicitly. But this is what d cosine theta is, sine theta, d theta. This is what they are in terms of the amplitude function. Remember, this is what this is how you do an expansion basically in the Legendre polynomials. And there's, the normalization just comes from the version of completeness for the P of L's. But that's not particularly important. What is important is that, you just have to recognize that you can always expand a function of theta in terms of these Legendre polynomials. And that's convenient because everything we have is expanded in terms of the partial waves. So, we have to expand this amplitude, angular dependent amplitude as well. And the other thing to note is that, okay, we solved this problem for, what do we do here? We solved the free particle, right, problem with no potential. We went through this argument and showed that far enough away, the solutions have this form. But if you think about it, if you have a scattering problem, right, you have a particle coming in, interacts with some potential, and it goes out. And far away, there's no potential anyway, right? So far enough away, it really is just a free particle solution. You don't actually have to just set the potential to 0. The potential is 0 far enough away. So we know that far enough away, the solutions are for the U's, our U solutions, they really are just given by AL, sine of KR minus L pi over 2 plus some phase shifts. And the phase shifts might depend on K, the incoming momentum. But this is what the solution looks like for R going off to infinity. Okay, so now we have everything kind of, we have everything in hand to figure out what's going on with the general solution and then the Schrodinger equation solution. So now we can actually do this comparison directly. So what does it mean? Far enough away, there is no potential. So any effects of the potential must be captured in whatever particular kind of solution you get, which only depends on this amplitude AL and then these phase shifts delta L. And we know also that the solution to the whole problem, with the potential far away has to have this form. So these two things, they must be related to each other. And that's what we're going to do. We're going to finally do the big connection where we connect the general solution to this solution of the Schrodinger equation, which we know must look like this far away from the potential. So that's what we're going to do. So let's finally compare. So okay, so we have our psi of r theta, which is equal to sum over L of, now let's write down the solution we would get from the Schrodinger equation, which is this guy, right? Divided by r. These are our u's, u over r, and this is all PL cosine theta. And this is supposed to be equal to, right, the asymptotic form, which now we're going to call A. That's this A right here. We're going to have overall sum over L. Now we have to expand our exponential. And it's convenient to expand the exponential in terms of, so again, we have to expand this EBI KR cosine theta. I showed you how to do that. It's just given by these guys. It's convenient to, though, not write it in terms of signs, but to write it in terms of complex exponentials. This guy, far enough away for KR much bigger than 1. This guy is, instead of writing the sign, you can write this as, follows. You can write this as e to the I KR. And then this minus L pi over 2 gives me a factor of minus I raised to the Lth power. And then you get a minus e to the minus IKR from the sign. And then the minus pi over 2 gives me an I raised to the Lth power. And then all of this is divided by 2IKR. So just writing the sign in terms of complex exponentials. Instead of writing it this way. So with that in mind, we write this part as 2L plus 1 IL divided by 2IKR. And then we have the e to the IKR minus I raised to the L minus e to the minus IKR I to the L. And then we have the part that comes from the scattered portion, which again are these f of L's, and it's the spherical wave going out, e to the IKR over R, and all of this is multiplied by PL cosine theta. Why did I do this? Because you see the incoming plane wave, it's not convenient to write it in terms of sign. It's convenient to write it in terms of the complex exponential, because the complex exponential will have a outgoing and incoming spherical wave. So a incoming plane wave is a combination, a delicate combination of incoming and outgoing spherical waves. And that's important because we have an outgoing spherical wave here. So you have to be sure to carefully kind of disentangle, when you're looking at just the whole solution, which part of the outgoing spherical wave is part of the incoming plane wave and which part is actually the scattered part. So that's the reason you kind of have to be a little bit careful with these things. And because again, the incoming plane wave contains within it a combination of incoming and outgoing spherical waves. So now we can just combine pieces and identify which parts are incoming and outgoing spherical waves. So we can do that. This becomes a sum over L. We can just start combining different pieces. One piece is 2L plus 1 over 2IKR plus F of L over R times e to the IKR. The I to the L's cancel for that part, because I times minus I is just 1. And then you have another piece, which is minus 2L plus 1. And there's a minus 1 raised to the Lth power that comes from the I squared over 2IKR. And this is e to the minus IKR. And this is all multiplied by PL cosine theta. Okay, so now we've taken our general asymptotic form of the solution, this one up here, and identified which pieces are the outgoing and incoming spherical waves. And now we can do the same thing to these guys. We can take, and let me now expand this guy. We can do the same thing with that guy, right? We can expand it in complex exponentials and figure out what the deal is there, right? So for that guy, you get a sum over L. You have AL, and now expanding in complex exponentials, you get 2I for the sign, 2IR. And here we get a minus I raised to the Lth power of e to the IKR plus delta L. And then you get a minus I raised to the Lth power of e to the minus IKR minus delta L. And that's PL cosine theta. And now again, we could break up into, well, we don't have to. We can already see what's going on. This part must be equal to this part, both proportional to IKR, and this part must be related to this part. That part's the outgoing, the incoming spherical wave. So you can identify immediately the relationships between the coefficients. First of all, we must have 1 plus 2IK F of L over 2L plus 1. That has to be equal to E to the 2I delta L function of K. And again, this comes, so we factor out, maybe we do one more step, I guess. We can factor out a factor of E to the delta L, or minus delta L. And then this becomes minus IL e to the I k r plus 2 delta L minus e to the IL e to the minus IKR. And then we could start comparing these guys to each other. And it's just some algebra. And from this first column, you get this relationship. These two terms have to be equal to the stuff in here. And that gives you this equation. And that's actually all you need. Then the other, you can make these constants equal to each other as well. But this, from the first column, from looking at the outgoing spherical wave, that's enough to tell you the relationship between the phase shifts, these delta LKs, and the coefficients of the scattering amplitude, the F. So yeah, so probably for the next homework, I'll make you sort of work out the algebra yourself in a little detail. It's not too bad. You just compare what's in front of these guys. Again, you set the coefficients in front of the e to the IKRs equal to each other. And then everything, and the reason you extract this is because you want to make sure that this guy doesn't depend on any phase shifts, because it has to just be equal to something simple in terms of these guys. So it's really the F's that depend on the phase shifts. So and of course the A's are also involved, but you get the idea. You have two equations, one from the outgoing wave and one from the incoming wave, and two unknowns. One is the delta L's and the other one is the AL's, and you just want to solve for those. And if you do that, you eventually get this relationship. You get this solution for the F of L. So if we rewrite this, this is also equal to F of L is equal to 2L plus 1 over 2IK e 2I delta L phase shifts minus 1, or 2L plus 1 over K, and then we can factor out an e to the I delta, and then the rest of it becomes a sine of delta L. And again, the delta L's depend on K. So this is it. This is the relationship between the scattering amplitude and the phase shifts. And the phase shifts you get by solving the Schrodinger equation, right? You solve the Schrodinger equation for a specific potential. You look at what does that solution look like far away. That's how you get the phase shifts. And then you can use those phase shifts and plug it back in to an expansion of the scattering amplitude. So let me say that. This is sort of the last thing. So the scattering amplitude, which is what goes into, remember the double boxed equation, this is the thing that tells you what the differential scattering cross-section is. Well, it's got to be plugging everything in, 1 over K, sum 0 to infinity, 2L plus 1, e to the I delta L, sine of delta L, PL cosine theta. That's very powerful. And moreover, you can integrate up the magnitude of F squared to get the total cross section. And so again, this thing squared, if I take this thing squared, that is equal to the differential scattering cross section. So then if I integrate it up, I get the whole cross section. You can use the properties of spherical, of Legendre polynomials to perform that integration and write everything in terms of the shifts. And what you'll get is that it's 4 pi or k squared. And again, I think it's worthwhile to have you work some of these things out yourself. Sine squared delta L. So again, this is very powerful, right? It's telling you that this is how those phase shifts are related to these measurable quantities, the differential scattering cross-section and the total scattering cross-section. If you know the phase shifts, which you get from solving the Schrodinger equation, you immediately know what the scattering cross-section is in the differential scattering cross-section from solving just Schrodinger's equation, which you know how to solve. So again, it's just just solving Schrodinger's equation, but just interpreting it in the proper way to get scattering cross sections and solve the scattering problems. So these are the sort of key formulas for partial wave expansion that tell you how to connect the solution of Schrodinger's equation to the actual measurable things. And the other important thing is if we look at the actual asymptotic solution again, and write it out in terms of the phase shifts now, it looks like follows. If we just solve for AL and so on, we write everything out in terms of we write out that asymptotic solution in terms of the phase shifts. Then you get the following thing. So you see here, this guy is multiplying the outgoing spherical wave. So what is important to note is that when there are no phase shifts, when these deltas are all 0, then this is just 1. And then this becomes just the partial wave expansion of a plane wave along the z direction. So it's really these phase shifts that modify the phase of the outgoing spherical wave that give you the sort of the contribution that occurs due to scattering from a potential. It's really the effect of the scattering is entirely embodied in these phase shifts. This is the and that'll lead us to a discussion of the so-called S matrix, and the Lth contribution to the S matrix is just this factor e to the 2I delta L. And again, all this depends on the incoming momentum. And we'll see that that'll be important. The fact that it's just a phase, so that the magnitude of this thing is always equal to 1, that'll be important. That'll be related to the difference between elastic and inelastic scattering. But we'll deal more with that, I guess, next time because I'm out of time. But these are really the main results of the partial wave expansion. And again, just conceptually, it's important to know what we did. We took the Schrodinger equation and we interpreted solutions to it as having the following asymptotic form: incoming plane wave plus outgoing spherical wave from the scattering. And then just by studying what the solutions of the Schrodinger equation look like for no potential, which is what happens far away from the target, we're able to understand how the scattering amplitude is related to a property of the Schrodinger equation solution, namely the phase shifts, which are just some coefficients you would get by solving the Schrodinger equation. And this is the relationship we got by doing that comparison. And then from that, we can immediately write down what the differential scattering cross-section is and the total scattering cross-section is in terms of those properties of the solution, the phase shifts. And that's the essence of the partial wave expansion.